weak electrolytes, we know that they dissociate partially. They never dissociate 100% in the solutions, right? So there's always an equilibrium there between the dissociated molecules and undissociated ones, right? So let's suppose we have the AB. AB is a weak electrolyte, and when you put it in a solvent, make a solution of it, and what you see that there is always an incomplete dissociation. Some of the molecules will dissociate and some remain as undissociated, right? And let's suppose the C is the initial concentration of the AB, and when the time is 0, at the start, when you put some electrolyte, you put some of the electrolyte in the water. C is the concentration of the electrolyte AB, and some of the molecules dissociate and some remain undissociated. So when the time is 0, initial concentration of the A positive and the B negative is 0. But once the equilibrium has been attained, so at the equilibrium stage, what will be the concentration of A and B? That will be C alpha, and B is also C into alpha. The concentration of the AB, which is undissociated at the equilibrium, that will be C into 1 minus alpha. And what is alpha? Alpha is the degree of dissociation, right? Alpha is the degree of dissociation, and that is equal to the number of the molecules that have dissociated, number of molecules dissociated, and divided by the total number of the molecules, right? The total number of molecules. So let's say you take 100, for example, you take 100 molecules, and out of the 100 molecules, let's say the 10 molecules dissociate, 90 remain undissociated. So therefore you can say alpha, there will be the 10 have been dissociated out of the 100, correct? So this is 10 by 100, correct? That will be the degree of dissociation. Now if you apply the law of chemical equilibrium here, let's apply the law of chemical equilibrium. We can say the equilibrium constant now here will be equal to the concentration of A positive, B negative here, divided by the concentration of the AB. And that means it is the concentration of C alpha is the concentration of A, into C alpha again the concentration of B, by C into 1 minus alpha, which you can write it C alpha square divided by 1 minus alpha. Okay, and over here I can take 1 minus alpha again equal to 1, because for a weak electrolyte, for a weak electrolyte, when we can say when alpha is very, very less than 1, right? Alpha in comparison to 1 is very less, so we can say 1 minus alpha is almost equal to 1. Therefore you can rearrange the above equation. You can say the K will be equal to C alpha square. So means that the K depends on the concentration and the degree of dissociation here. You can further rearrange. You can say alpha square will be K by C, okay, or you can say the alpha equals root of Kc, K by C, right? Okay, alpha equals root of Kc. So that means the degree of dissociation, actually you can see here, is inversely proportional to the concentration, correct? It is inversely proportional to the concentration. If the concentration decreases, that means the degree of dissociation will increase. So concentration is again written as 1 by V, right? 1 by V is the concentration, so that means you can rearrange. You can write down this equation also like K into V, okay, K into V, which means that if you have, suppose, an electrolyte in a given amount of the solvent, and if you are adding, suppose here, more solvent in it, you add more solvent in it, so that the volume of the solution will increase. Okay, now the volume of the solution increases by adding the solvent. When the volume increases, the alpha will decrease. The dissociation, the degree of dissociation will always increase with dilution, correct? So for any weak electrolyte, if you keep on adding this the solvent, so that the volume increases, the degree of dissociation will definitely increase. All right, hope you got it. Thanks for watching the video. Bye for now.